In functional analysis and quantum measurement theory, a positive operator-valued measure, POVM, is a measure whose values are non-negative self-adjoint operators on a Hilbert space, and whose integral is the identity operator. It is the most general formulation of a measurement in the theory of quantum physics. The need for the POVM formalism arises from the fact that projective measurements on a larger system, by which we mean measurements that are performed mathematically by a projection-valued measure, PVM, will act on a subsystem in ways that cannot be described by a PVM on the subsystem alone. POVMs are used in the field of quantum information. In rough analogy, a POVM is to a PVM what a density matrix is to a pure state. Density matrices are needed to specify the state of a subsystem of a larger system, even when the larger system is in a pure state. See purification of quantum state. Analogously, POVMs on a physical system are used to describe the effect of a projective measurement performed on a larger system. Historically, the term probability operator measure, POVM, has been used as a synonym for POVM, although this usage is now rare. Definition: in the simplest case, a POVM is a set of Hermitian positive semi-definite operators, opening curly bracket, F, I, closing curly bracket, display style, F underscore I, on a Hilbert space, H, display style, mathcal, H, that sum to the identity operator, I, equals 1, N, F, I, equals, I, H, display style, sum underscore, I equals 1, caret, N, F underscore, I, equals, operator name, I, underscore, H, closing curly bracket. This formula is a generalization of the decomposition of a finite-dimensional Hilbert space by a set of orthogonal projectors, opening curly bracket, E, I, closing curly bracket, display style, E underscore I, defined for an orthogonal basis, opening curly bracket, pipe, I, closing curly bracket, display style, left phi underscore I, right, wrangle, by, I, equals, 1, N, E, I, equals, I, H, E, I, E, J, equals, delta, I, J, E, I, E, I, equals, pipe, I, pipe, display style, sum underscore, I equals 1, caret, N, E underscore, I, equals, operator name, I, underscore, H, quad E underscore I, E underscore J, equals, delta underscore I, J, E underscore I, quad E underscore I, equals, left phi underscore I, right, wrangle, left, langle, phi underscore I, right, closing curly bracket. An important difference is that the elements of a POVM are not necessarily orthogonal, with the consequence that the number of elements in the POVM, N, can be larger than the dimension, N, of the Hilbert space they act in. In general, POVMs can be defined in situations where the outcomes of measurements take values in a non-discrete space. The relevant fact is that measurement determines a probability measure on the outcome space. Definition: let X, M, be measurable space. That is, M is a sigma algebra of subsets of X. A POVM is a function f defined on M whose values are bounded non-negative self-adjoint operators on a Hilbert space H such that f X equals IH and for every she display style in H E F E she display style E mapsto Langle F E she mid she wrangle is a non-negative countably additive measure on the sigma algebra M. This definition should be contrasted with that of the projection-valued measure, which is similar, except that for projection-valued measures, The values of f are required to be projection operators. Newmark's dilation theorem. Note: an alternate speaking of this is Newmark's theorem. Newmark's dilation theorem is a result that expresses POVMs in terms of projection-valued measures. It states that a POVM can be lifted by an operator map of the form V** V to a projection-valued measure. In the physical context, this means that the measurements accomplished by a POVM consisting of a weighted sum of n rank 1 operators acting on an n-dimensional Hilbert space, where one may typically have n greater than n, can equally well be achieved by performing a projective measurement on a Hilbert space of dimension n. So, for example, as in the theory of projective measurement, the probability that the outcome associated with measurement of operator f I _f_I occurs p I equals t r rho f I p I equals room tr rho f I backslash closing curly bracket, where rho rho is the density matrix representing the mixed state of the measured system. Such a measurement can be carried out by doing a projective measurement in a larger Hilbert space. Let us extend the Hilbert space H A displaystyle H underscore A to H A displaystyle H underscore A O plus H underscore A caret perp, and perform the measurement defined by the projection operators. Opening curly bracket pi caret I closing curly bracket displaystyle hat pi underscore I. The probability of the outcome associated with pi caret I displaystyle hat pi underscore I is p I equals t r rho pi caret I equals t r rho pi caret a pi caret I pi caret a displaystyle p I equals room tr rho hat pi underscore I equals room tr rho hat pi underscore a hat pi underscore I hat pi underscore a backslash closing curly bracket, where pi caret a displaystyle hat pi underscore a is the orthogonal projection taking h a displaystyle H underscore A O plus H underscore A caret perp 2 H A displaystyle H underscore A in the original Hilbert space H A displaystyle H underscore A. This is a POVM with operators given by F I equals pi caret A pi caret I pi caret A displaystyle F underscore I equals hat pi underscore A hat pi underscore I hat pi underscore A. Newmark's dilation theorem guarantees that any POVM can be implemented in this manner. In practice, POVMs are usually performed by coupling the original system to an ancilla. For an ancilla prepared in a pure state, pipe 0 b displaystyle 0 wrangle underscore b. This is a special case of the above. The Hilbert space is extended by the states pipe a pipe psi b displaystyle phi wrangle underscore a o times psi wrangle underscore b, where psi pipe 0 b equals 0 displaystyle langle psi 0 wrangle underscore b equals 0. Post measurement state. Consider the case where the ancilla is initially a pure state pipe 0 b displaystyle 0 wrangle underscore b. We entangle the ancilla with the system taking pipe psi a pipe 0 b I m I pipe psi a pipe I b display style psi wrangle underscore a 0 wrangle underscore b right arrow sum underscore I m underscore I psi wrangle underscore a I wrangle underscore b closing curly bracket, and perform a projective measurement on the ancilla in the opening curly bracket pipe I b closing curly bracket display style I wrangle underscore b basis. The operators of the resulting POVM are given by f I equals m I display style f underscore I equals m underscore I caret dagger m underscore I. Since the m I display style m underscore I are not required to be positive, there are an infinite number of solutions to this equation. This means that there are infinite different experimental apparatuses that give the same probabilities for the outcomes. Since the post-measurement state of the system rho single quote equals m I rho m I t r m I rho m I display style rho equals m underscore I rho m underscore I caret dagger over room tr m underscore I rho m underscore I caret dagger closing curly bracket depends on the m I display style m underscore I. In general, it cannot be inferred from the POVM alone. Another difference from the projective measurements is that a POVM is not repeatable. If rho single quote display style rho is subjected to the same measurement, the new state is rho quote equals m I rho single quote m I t r m I rho single quote m I equals m I rho m I t r m I rho m I display style rho equals m underscore I rho m underscore I caret dagger over room tr m underscore I rho m underscore I caret dagger equals m underscore I rho m underscore I caret dagger m underscore I caret dagger over room tr m underscore I rho m underscore I caret dagger m underscore I caret dagger closing curly bracket, which is equal to rho single quote display style rho iff m I 2 equals m I display style m underscore I caret 2 equals m underscore I closing curly bracket. That is, if the POVM reduces to a projective measurement, this gives rises to many interesting effects, amongst them the quantum anti-Zeno effect. Quantum properties of measurements. A recent work by T. Amri makes the claim that the properties of a measurement are not revealed by the POVM element corresponding to the measurement, but by its pre-measurement state. This one is the main tool of the retrodictive approach of quantum physics, in which we make predictions about state preparations leading to a measurement result. We show that this state simply corresponds to the normalized POVM element rho caret r e t r n equals pi caret n t r opening curly bracket pi caret n closing curly bracket display style hat rho underscore mathroom retr caret n equals frac hat pi underscore n mathroom tr brace hat pi underscore n r brace, closing curly bracket. We can make predictions about preparations leading to the result n by using an expression similar to Born's rule. P r m pipe n equals t r opening curly bracket rho caret r e t r n theta caret m closing curly bracket. Display style mathroom p left m vert n right equals mathroom tr brace hat rho underscore mathroom retr caret n hat theta underscore m r brace, closing curly bracket, in which theta caret m display style hat theta underscore m is a Hermitian and positive operator corresponding to a proposition about the state of the measured system just after its preparation in some state. Rho caret m display style hat rho underscore m. Such an approach allows us to determine in which kind of state the system was prepared for, leading to the result n. Thus, the non-classicality of a measurement corresponds to the non-classicality of its pre-measurement state, for which such a notion can be measured by different signatures of non-classicality. The projective character of a measurement can be measured by its projectivity. Pi n display style pi underscore n, which is the purity of its pre-measurement state. Pi n equals t r rho caret r e t r n 2 display style pi underscore n equals mathroom tr left hat rho underscore mathroom retr caret n right caret 2 right closing curly bracket. The measurement is projective when its pre-measurement state is a pure quantum state. Pipe psi n pi n equals 1 display style vert psi underscore n wrangle pi underscore n equals 1 closing curly bracket. Thus, the corresponding POVM element is given by pi caret n equals eta n pipe psi n pipe display style hat pi underscore n equals eta underscore n vert psi underscore n wrangle langle psi underscore n vert closing curly bracket, where eta n equals t r opening curly bracket pi n closing curly bracket. Display style eta underscore n equals mathroom tr braced pi underscore n r brace is in fact the detection efficiency of the state. Pipe psi n display style vert psi underscore n wrangle. Since Born's rule leads to p r n pipe psi n equals eta n display style mathroom p left n vert psi underscore n right equals eta underscore n. Therefore, the measurement can be projective but non-ideal, which is an important distinction with their usual definition of projective measurements. An example: unambiguous quantum state discrimination. Let us suppose that a quantum system, which we call the input, is known to be in a state drawn randomly from a given set of pure states. The task of unambiguous quantum state discrimination, UQSD, is to discern conclusively, at least sometimes, which state the system was in. The impossibility of perfectly discriminating between a set of non-orthogonal states is the basis for quantum information protocols such as quantum cryptography, quantum coin flipping, and quantum money. We will give a two-dimensional example in which using a POVM strategy has a higher success. probability for achieving UQSD than any possible projective measurement. First, consider a trivial case. Take a set consisting of two orthogonal states, pipe psi psi wrangle and pipe psi t psi t wrangle. A projective measurement whose corresponding Hermitian operator has the form a equals a pipe psi t pipe plus b pipe psi pipe display style hat a equals a psi t wrangle langle psi t plus b psi wrangle langle psi closing curly bracket will result in eigenvalue a only when the system is in pipe psi t display style psi t wrangle, and eigenvalue b only when the system is in pipe psi display style psi wrangle. In addition, the measurement always discriminates between the two states, i.e., with 100% probability, so we can achieve UQSD every single time. This is impossible for anything but orthogonal states. Now consider a set that consists of two states, pipe psi display style psi wrangle and pipe display style phi wrangle in two-dimensional Hilbert space that are not orthogonal, i.e., pipe psi pipe equals cos theta display style langle phi psi wrangle equals operator name cos theta closing curly bracket for theta greater than 0 display style theta greater than 0. These could be states of a system such as the spin of spin minus 1/2 particle, e.g., an electron, or the polarization of a photon. In order to make a quantitative comparison between different strategies, we make the a priori assumption that the system has an equal likelihood of being in each of these two permitted states. Then the best strategy for UQSD using only projective measurement is to perform each of the following measurements. Pi psi t equals pipe psi t pipe display style hat pi underscore psi t equals psi t wrangle langle psi t closing curly bracket. Pi t equals pipe t pipe display style hat pi underscore phi t equals phi t wrangle langle phi t closing curly bracket 50% of the time. Here the t indicates a vector orthogonal to the given vector, being projections. These observables have possible outcomes of 0 or 1. If the measurement pi psi t display style hat pi underscore psi t is performed and results in a value of 1, then it is certain that the state was in pipe display style phi wrangle. However, a result of 0 is inconclusive since this can come from the system being in either of the two states in the set. Similarly, a result of 1 for the measurement pi t display style hat pi underscore phi t indicates conclusively that the system was in pipe psi display style psi wrangle, and a result of 0 is inconclusive. The probability that this strategy returns a conclusive result is then p r o j equals 1 minus pipe psi pipe 2 display style p underscore mathroom project equals frac 1 langle phi psi wrangle 2 closing curly bracket. As we shall see, A strategy based on POVMs has a greater probability of success given by POVM equals 1 minus pipe psi pipe display style P underscore mathroom POVM equals 1 Langle phi psi wrangle closing curly bracket. This is the minimum allowed by the rules of quantum indeterminacy and the uncertainty principle. This strategy is based on a POVM consisting of f caret psi equals 1 minus pipe 1 plus pipe psi pipe display style hat f underscore psi equals frac 1 phi wrangle Langle phi 1 plus Langle phi psi wrangle f caret equals 1 minus pipe psi pipe 1 plus pipe psi pipe display style hat f underscore phi equals frac 1 psi wrangle Langle psi 1 plus Langle phi psi wrangle f caret I n c o n c l equals 1 minus f caret psi minus f caret display style hat f underscore mathroom in kinkle equals 1 hat f underscore psi hat f underscore phi closing curly bracket, where the result associated with f caret I display style hat f underscore I indicates the system is in state I with certainty. These POVMs can be created by extending the two-dimensional Hilbert space. This can be visualized as follows. The two states fall in the xy plane with an angle of theta between them, and the space is extended in the z direction. The total space is the direct sum of spaces defined by the z direction and the xy plane. The measurement first unitarily rotates the states towards the z-axis so that pipe psi display style psi wrangle has no component along the y direction, and pipe display style phi wrangle has no component along the x direction. At this point, the three elements of the POVM correspond to projective measurements along x direction, y direction and z direction, respectively. For a specific example, take a stream of photons, each of which is polarized along either the horizontal direction or at 45 degrees. On average, there are equal numbers of horizontal and 45-degree photons. The projective strategy corresponds to passing the photons through a polarizer in either the vertical direction and minus 45-degree direction. If the photon passes through the vertical polarizer, it must have been at 45 degrees and vice versa. The success probability is 1 minus 1 slash 2 slash 2 equals 25%. Display style 1 minus 1/2 2 equals 25%. The POVM strategy for this example is more complicated and requires another optical mode, known as an ancilla. It has a success probability of 1 minus 1 slash 2 equals 29.3%. Display style 1 to 1 sqrt 2 equals 29.3%. SIG POVM. Quantum T designs have been recently introduced to POVMs and symmetric, informationally complete POVMs, SIG POVMs, as a means of providing a simple and elegant formulation of the field in a general setting. Since a SIG POVM is a type of spherical T design, see also quantum measurement, mathematical formulation of quantum mechanics, quantum logic, density matrix, quantum operation, projection valued measure, vector measure. References: POVMs. J. Preskill. Lecture Notes for Physics, Quantum Information and Computation. http www. Theory. Caltech. Edu. People. Preskill. pH 229. #lecture. K. Krauss. States, Effects, and Operations. Lecture Notes in Physics 190. Springer. 1983. E. B. Davies. Quantum Theory of Open Systems. Academic Press. 1976. A. S. Holivo. Probabilistic and Statistical Aspects of Quantum Theory. North Holland PUBL. Sci. Amsterdam. 1982. POVMs and Measurement. M. Nielsen and I. Chang. Quantum Computation and Quantum Information. Cambridge University Press. 2000. Newmark's Theorem. A. Perez. Newmark's Theorem and Quantum Inseparability. Foundations of Physics. 12. 1441–1453. 1990. A. Perez. Quantum Theory. Concepts and Methods. Kluwer Academic Publishes. 1993. I. M. Gelfond and M. A. Newmark. On the Embedding of Normed Rings into the Ring of Operators in Hilbert Space. Rec. Math. Matt. Sabornik. N. S. 12. 54. 1943. 197–213. Unambiguous Quantum State Discrimination. I. D. Ivanovich. Phys. Let. A 123,257. 1987. D. Dykes. Phys. Let. A 126,303. 1988. A. Perez. Phys. Let. A 12819. 1988. Review articles on quantum state discrimination. A. Cheffels. Quantum State Discrimination. Contemp. Phys. 41. 401. 2000. http. arXiv. org. abs. quam/ph 0010114v1. J. A. Burgo. U. Herzog. M. Hillary. Discrimination of Quantum States. Lect. Notes Phys. 649. 417–465. 2004.